You ever look at your computer specs, 8, 16, maybe even more cores, and you just wonder, why isn't my software running 16 times faster? You are definitely not alone. It's a super common frustration that actually gets to the heart of a really deep, kind of complicated problem in modern computing. So let's get into it.
And this quote right here, from a developer on Reddit, just sums it all up, doesn't it? It's not about being lazy, not at all. It's about this fundamental, almost secret complexity in how our computers actually get things done. The frustration is so real, and it all comes from this gap between how we think computers should work and how they actually do.
So that's the big question, right? If it's not the developers, then what is it? And the answer is pretty fascinating. It's buried deep inside the architecture of the very chips we use every single day. Turns out, to get faster, our computers, well, they have to kind of bend the rules of reality a little bit.
To really get this, we first have to understand the lie, or, maybe simplification is a kinder word. We all have this mental model of how a computer works, but the hardware itself, it has a secret life that's way, way messier.
Now, this is the simple view we all have in our heads, right? You picture a bunch of processors, your cores, all just neatly dipping into one big pool of shared memory. Core 1 writes something, Core 2 reads it. It's simple, it's direct, it makes perfect sense. And it's a totally reasonable way to think about it.
And that simple model leads to a really basic assumption for any programmer. The code runs in the order you see it on the screen. You write line A, then line B. You expect the computer to do A, then B. We call this program order, and it's the bedrock of logical thinking in software. But what if I told you that's not what's really happening under the hood?
And here it is, the first crack in our nice, simple model. Just like this user points out, every single core has its own tiny, lightning-fast memory called an L1 cache. Think of it like a personal sticky note. And the key part is, these sticky notes aren't magically in sync with each other. Core 1 can be scribbling away on its note, and for a brief moment, Core 2 is completely in the dark about what's changed.
So why? Why would the hardware create this potential for chaos? Well, it's for one reason: raw speed. To squeeze every last drop of performance out, the hardware and the software that turns your code into ones and zeros are doing some unbelievable gymnastics. They're reordering instructions, they're buffering writes, they're pipelining operations. All of it is to hide delays and keep things moving. This is not a bug, it is absolutely a feature, a very powerful but very complicated one.
Okay, so if the hardware is just constantly shuffling the deck behind our backs, how can anyone write code that actually works? Well, there's a rulebook. It's a formal contract between the programmer and the processor that says exactly what kind of shenanigans are allowed. And this rulebook is called a memory consistency model.
This contract is everything. It's the absolute ground truth. It doesn't tell you how the wires are laid out. It tells you about the behavior you're allowed to see. It's the hardware telling the programmer, look, even with all our secret optimizations, we promise you will never see a result that breaks these specific rules.
Now, the most intuitive and strictest rulebook is called sequential consistency. It basically makes a two-part promise. First, everything that happens across all the cores will look as if it happened in one single global timeline. Second, in that timeline, the steps for any one core will stay in the order you wrote them.
To put it really simply, sequential consistency is the what you see is what you get model. It's the behavior we all just naturally expect. It's clean, it's simple to think about, and, as you've probably guessed, forcing a modern processor to follow these strict rules all the time would make it painfully slow.
So let's actually see what happens when a processor decides to play by a looser set of rules to get more speed. We're going to walk through a classic computer science example that shows this off perfectly.
Okay, here's the setup. Super simple. We've got two threads running on two different cores. Two variables, x and y, and they both start at 0. Thread 1 is going to read x, then write a 1 to y. At the same time, thread 2 is going to read y, then write a 2 to x. So, the big question is it possible for thread 1 to end up reading a 2, while thread 2 ends up reading a 1?
So if we follow our strict sequential consistency rules, let's see what can happen. Let's say thread 1 goes completely first. It reads x, which is 0, and then writes 1 to y. Then thread 2 gets its turn. It reads y, which is now 1, and writes 2 to x. The final score? R2 is 0, R1 is 1.
Okay, let's flip it. What if thread 2 goes first? It reads y, which is 0, and writes 2 to x. Then thread 1 wakes up. It reads x, which is now 2, and writes 1 to y. The result this time? R2 is 2, R1 is 0. Again, totally logical. You can mix these steps up in a few other ways, but you always get a result that makes sense. And this is the critical point. No matter how you arrange these steps, as long as each thread follows its own internal order, it seems impossible to get that target result. For R2 to be 2, step 4 has to happen before step 1. And for R1 to be 1, step 2 has to happen before step 3. If you trace that out, you get a circle, a logical paradox. It just shouldn't be possible.
And here's the punchline. On many of the processors sitting in our computers right now, this impossible outcome is not only possible, it can and does happen. The hardware's relentless quest for speed leads it to break the simple, intuitive rules we thought we could count on.
How? How on earth does that work? How can both threads manage to read the new value written by the other guy before their own write has even been seen by anyone?
The culprit is an optimization like a write buffer. Just imagine each processor has an outbox for its writes. Instead of waiting for that write to go all the way to memory, which is slow, the processor just shoves it in the outbox and immediately moves on to its next task, in this case, the read. So thread 1 can drop its write to Y in its outbox and then immediately read X, seeing the value that thread 2 just wrote. Both cores can do this at the same time, and bam, the impossible just happened.
And this brings us right back to the programmer. They're the one caught in the middle of this huge conflict between making things simple and making things fast. This is the programmer's dilemma. This slide just nails the core trade-off. On one side, you have the nice, simple rules of sequential consistency. They're easy to think about, but they basically tie one of the hardware's hands behind its back. On the other side, you've got these weaker, more relaxed models. They unleash the processor's full performance, but they force the programmer to deal with totally bizarre, counterintuitive stuff like the example we just saw.
So how do developers even survive this? They use special tools designed to manage all this complexity. You've probably heard of things like mutexes or locks. As this comment explains, these tools are basically prepackaged commands that tell the hardware, hey, listen, for this one little part of the code, stop with the sneaky optimizations. I need you to enforce some order right here, right now.
You can think of a memory barrier like a big stop sign in the code. When the processor sees it, it knows it has to finish everything before the stop sign before it's allowed to start anything after it. It forces that outbox to get flushed. This is how programmers carefully and strategically put order back into the chaos, but only where it's absolutely critical. That way, the hardware can run at full tilt the rest of the time.
And this really brings us to the final thought. That contract we've been talking about, the rulebook, well, it's getting thicker and way more complicated with every new processor generation. We want more speed, so that needs more optimization, which then needs more complex rules. So the question we're left with is this: are we heading to a future where the contract between the silicon and the software just becomes too complex for us humans to really manage effectively? That's the central challenge for the next era of computing,